Okay, then let's get started. So welcome back to the diffusion and diffusion models. So we're gonna continue the discussions for the basics of the diffusion models today. So from the last time, what we are discussing is that basically what we want to do is like all about basically modeling the marginal data distribution, right? So basically it's all about basically how we're gonna model this kind of the marginal distribution. And the basic idea for that is to basically model the prior distribution, which is typically defined as the standard Gaussian distribution. And it's also all about how we're gonna basically learn some kind of the proper likelihood distribution in a way that this combination can model the marginal distribution. And the question is that how we are going to basically learn the likelihood the distribution only by just having some kind of a set of the samples from this distribution. And for that, the idea that we have seen in the VAE case is to basically jointly learn both the likelihood distribution, which is also represented with the decoder, and also the variation of the posterior, which is this part, which is also basically represented with the encoding the network. So that was the basic idea. And also the limitation that we have seen for the VAE is that basically everything is the Gaussian, right? So especially for the likelihood distribution, we are also modeling this part as kind of the Gaussian distribution in a way to basically have the fixed the variance and also only predicting the mean using the decoding the network. And this is basically limiting some kind of the expressibility for the marginal distribution because the marginal distribution will be basically represented as the combination like these two. And now these each of these two, both of them are basically modeled as the Gaussian distribution. But the complexity of the data distribution here that we are having might be something that might be too complex to be expressed with the combinations of the two Gaussian distributions. So here the question is that how we are going to basically design the new genetic model in a way that this likelihood distribution becomes something more complex, right? Not just the Gaussian distribution, but something that is basically the more complex the distribution. So for that, we started to discuss the basic idea for the some diffusion models, starting from the recursive VAE in terms of basically having some multiple the layers of the latent the variables. And from that, we also started to discuss the diffusion models. So the very basic ideas for the diffusion model is that we are basically having some kind of the sequential processes starting from the data point from the x0 there all the way to the x capital T. So as I also mentioned from the last lecture, so these are the notations that we are going to use for now. But as I also said, we might also need to change the notations later. But here, basically, you should basically remember this. The x0 indicates the sample of the clean data point, right? The data point that we have. And x capital T here is basically the sample from the unique Gaussian distribution. So that's the kind of the final, the latent the variables, right? And then we are also having some kind of the bunch of some intermediate, some latent the variables as well, from the x1 to the all the way to the xt minus 1, right? And both for the mapping from the data point to the final the latent variable, and also for the other way around, we are having some kind of the sequential process, which is basically going from this way and the other way around. And actually, also the mapping from the x0 to the x capital T will be called as kind of the fold process. So that's the process that we are. So let's see, like this is kind of the indicating kind of the time step, right? When you see that this T is kind of a time step, the process that we are increasing the time step is the fold process, mapping the data point to the x capital T, the final the latent variable, and the other way around will be called the reverse process. So that's kind of basic thing. And also the key idea for the diffusion model is that we are basically predefining the fold process, basically defining all the transition the distribution for the fold process into some kind of a specific form in a way that we don't need to learn the fold process. We are only going to learn the reverse process. So that's the basic idea in terms of like making it like easy to train the neural network. And one more thing is that, as I also mentioned the last time, we are going to define all the latent variables in the same dimensional space. So we are basically matching the the dimensions for all the relation, the variables, and also the data points as well. So this was kind of the basic setup for the diffusion models. And also, we started to see some one specific version of the diffusion models. So these are some kind of some specific kind of the way to define the diffusion models. But the thing is that in this class, we are also going to be discussing kind of the different versions or different kind of the models, some kind of specific models in the diffusion, in the family of the diffusion models. So we're gonna see that actually this is kind of like the one version, and we are also going to discuss some the other versions in the other lectures. And this is basically the basic model. And also your assignment one will be, the part of the assignment one will be basically implementing the basic model. And you're gonna see that actually it quite works well. So for this kind of the basic model, what we are going to assume is that both the forward and the reverse processes will be defined as kind of the Markovian processes, which means that in the forward process, like when you iteratively like sampling each of the xt here from the previous step, the xt minus 1, the xt will only depends on the right before the 1, the xt minus 1, not depending on the previous the states. So when you see this kind of some conditional distribution, sampling xt conditioned by the xt minus 1, the x0, we can easily drop this part because we know that by the hourly definition, xt is not dependent to the x0 here, right? So we can basically easily drop the x0 here. So that basically makes it easy to basically define all the other kind of things, right? And also, we are going to specifically define the fault, the transition, the distribution into this kind of the way. So you can say that this is basically defined as kind of the Gaussian distribution. And you're going to see that we are defining many things into the Gaussian. Otherwise, I mean, there are actually the other versions in terms of like not defining this into the Gaussian, but something else. But we're going to make it simple in terms of like making it like Gaussian. We have some kind of some parameters here. So here, basically, the beta t is the parameters, which is the non-decreasing function over time. In terms of that, is basically having some numbers in the range from the 0 to 1, while keep increasing over time. So you can see that it's kind of the process that we are somehow injecting the noise, right? You see that this is the Gaussian distribution, while taking the xt and the multiplied by these parameters kind of center, which means that we are slightly shifting the xt minus 1 into some kind of scale. So this scale factor is 1 or the smaller than the 1, right? So if the beta t is basically 0, you can see that this is kind of the Dirac delta distribution in terms of that the sampling of the xt should be the same with the xt minus 1, right? But as we keep increasing the beta t, we can see that it's basically slightly moving this xt minus 1 into the center, the origin of the coordinate system, while basically adding some kind of the Gaussian noise, right? So you can see that this is kind of the process that we are iteratively injecting some kind of the noise into some kind of the data points, which means that the reverse process is the opposite, right? So that will be the process that we are iteratively deducting, removing some kind of the noise from some kind of the pure Gaussian noise. So actually, you can see that the generation process of the diffusion model actually can be seen as kind of the denoising process. We are gradually removing some kind of the noise, starting from the pure unique Gaussian noise in a way that is basically mapped to the clean data point. So this is basically the very specific way to define the default, the transition, the distribution. And then, as I said, the later lectures, we're gonna see the other ways to define the same default, the transition, the distribution. But basically, so why we are defining the full transition distribution in this way? So what we can say is that, so from this kind of the definition of the full process, what we are going to do is that we are also going to find the reverse process in a way to basically maximize the elbow function. So in the same way, I'm basically minimizing the negative the elbow function, right? So here the question is that how we can basically define the reverse process in a way to basically minimize this negative the elbow function, right? So we have seen how we can decompose this complex the elbow function into the 3 terms. And the thing is that after we decompose this into the 3 terms, what we can say is that, yeah. So basically, we are having these three. And the first term is the same, the reconstruct term that we have seen in the VA case. And this is only for the very last step in the reversibility process. For example, the x0 from the x1. So actually, this is like comparable. This is like compared to the other kind of the loss terms. This is like much smaller kind of terms in terms of the magnitude. So in practice, we can simply ignore this part in the loss function. And the second thing is that, so for this like the priority matching term here, the good thing of like defining the fold, the transition, the distribution in that way that we have seen in the previous slide is that the good thing for this definition is that it naturally basically minimizes this to be zero, right? Especially in the case like when you have some kind of the lots of kind of the time steps. So as we basically have some kind of the time steps in the both the fold and the reversibility processes, we can see that this will goes down to the zero by our the definition of the fold, the transition, the distribution. So that is kind of the reason like why we are defining the fold process in that way. So which means that we are going to ignore this part, and we don't need to care about this part because like this will go down to zero naturally by the definition of the fold process. So the only thing that we need to care about would be this part, right? So basically how we are going to define this. You can say that this is the sampling the xt minus 1 from the xt. So that's the reverse transition the distribution. So for each of the consecutive steps of the reversibility process, this is the sampling like the intermediate variable from the previous one, which is the xt here. So here all the question is basically how we are going to define this one, the transition, the distribution in a way to basically minimize the term of the loss function. So that's basically what we are going to see. So see, again, this is the same, the denoising the matching term, with minimizing the KL divergence between these two the distributions. And you can see that actually after rewriting all this the loss function, we can see that this reverse the transition the distribution actually should be the same with this form of the conditional distribution. Doesn't look that kind of like natural in terms of the we are sampling the xt minus 1 conditioned by both the xt and the x0. And we're going to get into that, like how we're going to basically derive some kind of closed form of like this distribution. But basically what you can say is that we need to define the reverse, the transition, the distribution in a way that this basically matches this distribution. That means basically we need to know how this distribution would look like, right? So that's kind of the key point. So before we get into that, so let's see how we can basically derive some kind of a closed form of like this distribution. So what we can say is that using the base rule, if you basically ignore the x0 here, x0, 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 you can see that this is exactly the base rule of the form, right? So based on the base rule, actually we can see that these can be basically decomposed into these three terms like this. Makes sense? If you basically ignore this x0 part, this is exactly the same form of the base rule, right, that we have seen in the previous lecture, right? So which means that this is the same with the multiplication, like those kind of three terms. And then now these are all some kind of some familiar some distributions, right? As I mentioned in the previous slide, for this distribution, we can ignore this x0, right? Because of we are assuming that the fold and reverse the processes are basically the Markovian process, which means that sampling the xt would not depend on the x0, right? So we can drop the x0. Then we can see that this is the fold, the transition, the distribution that we have already defined. Right? This is basically what we know. And also in the previous lecture, we have seen how we can derive the closed form for this. Do you remember how we derive these things? So actually, that's the first quiz. So before we get into some more details for this, based on the definition of the fold process here, and also how we define the alpha t hat here, let's basically see how we can derive the closed form of all those three terms. So continue. So if we see how these are derived, so these are basically all the things that we have seen in the previous lecture, right? So this might be also the confusing that we are introducing the beta t, which was basically parameter defining the full transition distribution. And then we are also defining the alpha t and the alpha t hat, like these are some kind of new parameters, but actually these are all connected to the beta t, right? So actually, you need to really see how these are basically defined, because these are really something that we're gonna keep seeing for the rest of all the lectures in this class. So please keep this in mind in terms of that. But here the key thing is that once we define the the transition distribution, based on that we can derive the closed form of the things that I'm going to call as kind of the fold jump the distribution, jumping from the x0 to the xt, right? And the thing is that this is also defined as kind of the Gaussian distribution. And then we started to see this distribution because basically this is something that we need to match using our reverse the transition distribution. And then after also some kind of the slightly dirty math here, what you can say is that based on all the closed form of these three distributions, after doing all the kind of the derivation, what you can say is that it turns out to be that this distribution is also another the Gaussian distribution, which the mean and the variance are basically defined in that way. So now we can say that interesting that everything is basically Gaussian here, but now we have some kind of the slightly more the complex of the mean and the variance here. So these are basically the main kind of the distributions that we are going to see in the fold process. As you have seen, this is basically something that we defined, right? The transition distribution. Based on that, we derived this. This is the jumping distribution. So let me go one by one. So this is basically the distribution that we defined for the two consecutive the latent variables. Now we can sample the xt from the xt minus 1. And this is something that we defined, right? And based on that, now we also could derive the closed form for this, something that I call the fold jump distribution, like jumping from the x0 to the xt here. So which means that without really doing any iterative process in the fold the process, we can directly sample xt from the x0. So that's something that you really need to remember. While we will need to do the iterative process in the reverse degenerative process, in the fold process, actually, we don't need to do any kind of iteration. We just need to we can directly sample the xt from the x0. So that's also kind of the one interesting point, right? And what we just basically defined, derived, was basically sampling the xt minus 1 by seeing both the x0 and the xt. So that is kind of interesting because like without the x0 here, if we didn't have that where is it? No. Yeah, if we didn't have the conditioning the x0 here, that's exactly the reverse transition process, right? Sampling the xt minus 1 from the xt. But here the thing is that what if we have not only the xt, but some kind of the provisioning x0 that was kind of some future kind of things in the reverse process, right? So in the kind of the reverse process, we're gonna only have the xt information and sampling the xt minus 1 from this. But what if we have both the xt and also the x0? So that's kind of the future output in the reverse process. For those cases when you have the conditions of like both of them, now we can have the information about some closed form of the distribution, which is another the Gaussian distribution. So these are basically some key 3D distributions that you need to remember in the fold process. And also the thing is that for the mean and the covariance of this Gaussian distribution, the good thing is that for the covariance, the matrix, these are something that we can just like calculate, right? We define the beta t, and based on that, we can also calculate those two things, which means that we can just directly calculate the covariance, the term in this Gaussian distribution. But how about the mean? For the mean, we also have some kind of some coefficients here that we can calculate. And you can see that actually the mean becomes some kind of some linear function taking both the xt and the x0. So that now we can basically see that the Gaussian distribution here can be basically defined as some kind of the mean function taking the xt and the x0 and the variance here, which we can just like directly compute. And do you remember like why we are seeing this distribution? This was the distribution that we wanted to match using the reverse differential distribution, right? So in terms of like minimizing this loss function, the question is that basically how we are going to model this reverse differential distribution in a way to minimize the KL divergence with the probability distribution, right? Then how should we model this? Now this question is quite simple, right? How should we model this? We know how this looks like, right? This was the Gaussian distribution. Even we know the variance, right? The only thing that we need to know, we don't know for this term is basically the mean function, because the mean function is basically involving the x0, while we do not have the x0 information, the reversible process. Which means that in terms of basically the modeling the reverse differential distribution, what we just need to do is that we will just need to also make this reverse transition distribution as the another the Gaussian distribution, obviously, because like we want to basically match this to this one. And since we want to match this to this, we can set the same the covariance here, right? Set the same the covariance. And the only thing that we need to learn using the neural network is actually this like the mean. Because here the mean was computed based on the x0, but while we don't have the x0 information, right? So this is the only information that we need to predict using the neural network. So that's the basic idea. So when you basically model the reverse differential distribution into this way, then what we need to do is that we need to basically minimize the KL divergence between these two, right? So if we also recall like what we have seen with the KL divergence, in the case that like when you have the two Gaussian distributions like this and this, especially for the same the covariance here, what's the KL divergence between these two? Do you remember? No, yes. This is actually what we have seen. This was the quiz last time, right? So you can check out the lecture slides there. So if you basically compute the KL divergence between these two distributions, when you match the covariance term here, then actually what we can say is that this becomes nothing but just like the L2 norm of the difference for these two the means of the two distributions. See? You need to check out how exactly we derive this, right? But basically, you see the basic idea. What we just need to do is that in the expected value, so basically we are computing the expected value for the arbitrary time t and also the x0 and the sample of the xt, right? Given this kind of sample of the x0 and the xt, in the training time, we will be able to basically compute the mean of this distribution, given the sample of the xt and the x0, right? And then what we are going to do is that we are basically modeling this reverse transition distribution as the Gaussian, and then we just need to basically minimize the L2 difference between these two the means here. So this is basically the mean that we are calculating from this, and this is basically the mean predictor for the reverse transition distribution. So typically for the mean prediction in neural network, we are feeding the xt and also the time step t as well. So given this like two information, we need to basically predict the mean of like this distribution in a way to basically minimizing the L2 loss for the arbitrary samples of the x0 and the xt here. Great. Yes. And then also typically in practice, there are some kind of the weighting term here. You can really just like put this like weighting term here, but in practice, many people just like ignore this term because like without even the weighting term, it still works well. So the very interesting thing here is that after like all this kind of the derivation, like seeing like how we define the default process and how the elbow function can be decomposed and also the minimized, after all those kind of things, the interesting point is that it turns out to be that the training of the mean prediction in network becomes pretty simple. Actually, this will be something that you need to implement in your the assignment 1. And you're going to see that actually this is really just like few lines of the code in the PyTorch. So basically, this is something that we are going to minimize, right? Expected value over the time t, and also the x0 for the samples of x0, and also the sample of the xt here. And then basically minimizing the expected value for this, right? Then we can either just like follow like one by one. So we are just sampling the x0 here, and then sampling the time t, and then what's the meaning like this? This is basically sampling the xt from this distribution, right? Because you can say that this is kind of the reparameterization of this Gaussian distribution, right? Yeah, so this becomes basically just like nothing but sampling the xt given the x0 and the time t here. And then what we do is that we just like compute this mean using this our sample of the xt and the x0, and then we predict the mean using the mean predictor, and then run the backpropagation while minimizing this L2 loss. Make sense? So actually, if you understood all the details, all the basics here, this is actually quite surprisingly point in terms of that after like all those kind of the derivations and everything, it turns out to be that the neural net training becomes very simple. It's really just like few lines of the code. So now you can see that how we carefully designed all the default process, and also how we carefully decompose the elbow function in a way that the like modeling the reverse the transition the distribution becomes just like learning the Gaussian distribution, and also especially just like learning the mean of the Gaussian distribution, and becomes like quite simple. Any questions on this?
Before you said that 3A is because it doesn't just normal distribution, but it looks like it also follows the Gaussian distribution too. Is it right?
That's the really good question, and we're gonna get back to that point later. Yeah, that's a really good point. Any other questions? So here the things that you need to basically see is that why we define the full process in that way, and why we see this kind of the decomposition of the elbow function. So all the basically the kind of things that we are seeing here is to basically make it easy to model the reverse transition distribution, and also make it easy to learn the proper the reverse transition distribution. So after all those kind of things, what we are seeing is that even we can directly compute the variance term in the reverse transition distribution. The only thing that we need to learn is basically the mean of the distribution. And like learning the mean becomes such a simple, just like sampling the x0 and the time t, and sampling the xt, like sampling x0 and the time t and the xt here, and then basically computing this mean, and also getting the prediction of the mean predictor, and minimizing the L2 loss in the backpropagation. So that's kind of the interesting point of the diffusion models, like everything is quite clear. So here, just like one more thing is that, so I introduced the idea that we are basically predicting the mean of the reverse transition distribution, right? But we know that we know the formulation of the mean actually, right? That was basically the function of the xt and the x0, right? So what we can do is that instead of like directly predicting the mean here, we can consider just like predicting the x0 given the xt. So what if we consider not the mean predictor, but the x0 predictor here, in a way that we can compute the mean from the xt and the x0. Well, what's the x0 here? x0 was one of the training the data point, right? Basically the clean data sample. While the xt is some kind of noise data, the point after we injecting some kind of noise, right? So that's kind of thing. So now we can consider having some kind of a clean sample, the predictor, which is predicting the x0 from the xt, instead of basically directly predicting the mean here. So that's the kind of just like the option. So what happens with the clean sample, the predictor, is that actually it becomes the same in terms of if you basically also derive all the things, then you can see that the elbow function, especially like this, the matching term here, becomes the same in terms of that we are still minimizing the L2, the difference between these two, with some kind of the new weight term here. And also here, we are going to simply ignore the weight term. You can really just like put the weighting term there. But in practice, even without the weighting term, actually it works well. Then it means that now we can do the same thing in the training time. Now we can basically have some kind of the clean sample, the predictor, the x0 predictor, while matching the x0 here. And at the end, like in the generation the process, we just need to compute the mean from the prediction of the x0. So that's the same thing. Then the question might be that, so what's the meaning of like predicting the x0 from the xt? So what you can see is that, so from this loss function, what we are basically doing here is that given the xt, so xt was a sample from given any kind of x0 here. But what we are doing is that using this loss function, we are basically predicting some kind of some expected value of the x0 that would result in basically sampling the xt from it, from the jump the prediction. So actually, if we see the real some kind of the generation the process, so this is kind of the 1D example. You're gonna see that this is kind of obviously the prior the distribution, the Gaussian the distribution, and let's say that this is kind of some complex some kind of the data distribution. So we're gonna basically start like sampling the x in the forward process. We're gonna start basically sampling some x0 here, and then adding some kind of noise in a way to make some kind of some sort of the trajectory of the xt all the way to the x capital T here. And as you can see that from the arbitrary the xt, actually there can be some multiple possible x0 that would result in basically reaching to this point through the forward process. Right? And what we are doing with the x0 the prediction here, basically with this loss function and also this network, is to basically predict some kind of the expected value, some kind of the average value of the x0 that would result in basically sampling the xt from the forward process. Make sense? So if we consider this like the clean sample the predictor, the interesting point is that actually if we recall the kind of the goal of the kind of the diffusion model is that we are going to basically sample the x0 in a kind of the iterative way, right? So that's kind of the idea of some kind of recursive kind of the sampling in the diffusion models. So starting from the x capital T, we are recursively basically sampling the xt minus 1, t minus 2, all the way to the x0, right? Which means that at the intermediate step, we don't know what sort of the x0 that we're gonna get. It's the iterative steps, right? But the interesting kind of thing with the clean sample the predictor is that every time in every intermediate step of the xt, actually we are seeing some kind of the expected value of the x0. And that means that the sampling of the xt minus 1 is actually based on some kind of the prediction of the final output of the x0. So every time from the xt, we are seeing basically what we are going to get at the very end of all the reversibility process. And based on that, we are not just taking the final output, but just taking the next step, sampling the xt minus 1. So that means that we are basically somehow defining our kind of some expectation of the final output every step. And we are not just directly taking that expectation, but just like based on that, we just like go one more step, xt minus 1, And then also basically defining our kind of prediction and also doing the iterations, right? So that's kind of the interesting the point of the diffusion models. So we can interpret the diffusion model as kind of like defining the process of the final the prediction of the expected the value for the x0 here. It is clear. So let me first show this. I think it might be good to show this first. So this is like one example of the image generation. So you can see that at the very beginning, we are starting from some kind of the unique Gaussian denoise, right? And over time, we are seeing some kind of the denoise the outputs. So because like we are following some kind of reverse process of like injecting the noise, right? So if we visualize the xt, then you're gonna see that it's like gradually denoising the all the intermediate the variables here in a way that we are getting to the x0. But actually, if we see visualize the prediction of the x0, so every time at the xt, we can consider basically predicting the expected value of the x0, right? We can also visualize that. Then you can see that it becomes like, every time we are seeing some kind of the blurry the outputs of the final kind of things, right? While basically refining every step. So we are not just directly taking the x0 prediction in the intermediate step, but based on the final the output, we just like go one more step and then refining this and also the going one more step, right? Actually, this is kind of the life lesson. I mean, for all the things that we do, actually, we also need to do this kind of training. So before we really go like some like step by step, we just need to first basically visualize what we wanna end up getting at the end of all the process, right? Based on that, we need to do some kind of planning, right? And diffusion model is really doing this kind of thing. Getting the prediction for the final the output, and just like going one more step and just like repeating these kind of things. So that's the idea of the clean the sample the predictor. So this can basically replace the mean prediction. So instead of like directly predicting the mean, we can consider predicting the x0. So that's the idea. Actually, the thing is that we can do one more thing. So the one more thing is that so this was the case that we are basically sampling the xt from the x0 first, right? And based on these two samples, like we are also sampling the xt minus 1 as well, right? So if we see basically how we compute the sample of the xt, actually the xt can be seen like this, right? So sampling the xt from this the jump distribution can be seen as we're computing this with some kind of the standard Gaussian the noise here, right? With the reparameterization is basically the same. So which means that so now we can define this epsilon t, which is now defined based on the xt and the x0. So the meaning of like the epsilon t is the standard the Gaussian noise that results in basically the jump from the x0 to the xt, right? So you can define the epsilon t as kind of the with the xt and the x0 here as well, right? So now what we can do is that even we can also consider redefining this kind of the mean function, not with respect to the xt and the x0, but with respect to the xt and then epsilon t. Can you quickly write down like what we're gonna get with the for the mean function for these two terms? this is not something that you need to submit. So let me continue. But yeah, you can check out that if you just plug in the definition of the epsilon t, then you're gonna see that actually it becomes like this, right? So that means that actually we can also define this like the mean function with respect to the xt and this epsilon t, right? Then you can feel that now we can also define the new predictor, right? That means instead of like also having the mean predictor and also the clean sample the predictor, now we can also consider the other one, which is the noise predictor, which is predicting this like standard Gaussian the nodes, epsilon t, in a way that we can just like compute the mean based on the xt and also the prediction of the noise. And then it's the same, all the things kind of thing, the same thing in terms of it becomes also the same, the L2 loss term with some kind of the another, the weighting term here, which we're gonna also ignore in the practice. Then you can see that this also becomes like all the same. We are just simply replacing the mean predictor into the clean sample the predictor. And also now this is the case that we are replacing that into the noise predictor, right? So the other kind of the cases. So you can see that actually there are a bunch of the options here, right? We have seen the three options. This is the natural option in terms of that we directly predict the mean of that the noise, the reverse the transition, the distribution, right? Most kind of the natural kind of the option. But instead of directly predicting the mean, what you can do is that we can consider predicting the clean sample. And this becomes the interesting idea in terms of that now we are kind of like foreseeing the output. And based on that, we basically decide the next step. So that's kind of the basic idea. And this is actually really key idea in the diffusion models. So what we are even going to see probably after the midterm week is that, so you can see this is kind of like making some sort of the trajectory. Starting from the x capital T all the way to the x0, we are making some kind of the trajectory in the space, right? And every time we are basically forcing some kind of the final destination, final output. And what we can do is that based on the final output, the expected output for that, we can see whether this is kind of the right trajectory that we want to go, which means that we're going to eventually go to some kind of the clean data point, basically realistic data point. But that may not be something that you want. You might have some kind of the conditions or some kind of the constraints. For example, I don't know, like you might want to, what should I say? You might want to basically make some kind of the red car, not just the car, but somehow all those kind of like red car, the condition, that's some kind of a very specific kind of the types of the output that we want to get, right? But then what you can get is that based on some kind of the forecasting of the final output, if that is basically not close to what we want to see, based on that, we can consider basically adjusting the trajectory. So that's kind of the interesting aspect of the diffusion models. We can do some kind of provide some kind of the guidance in the trajectory of the generation based on the prediction of the final output. So that's the kind of thing. And one more thing is basically this like epsilon t prediction, which is the noise prediction in this case. So there are basically these three options. And whatever we predict using the neural net, what we will need to do in the kind of reverse process is to basically compute the mean of this like reverse the transition distribution based on those kind of formulations, and then doing some iterative sampling. And as you can see, basically for one of those kind of things, given the xt, whatever you have the mean or the x0 or the epsilon t, given one of those kind of things, you can also compute the other things. Which means that even when you have some kind of the mean predictor or the noise predictor, based on that, you can also compute the expected, the final output as well, right? And you can also compute the noise from this like the mean, the clean sample, the predictor, right? So those are basically some kind of interchangeable kind of things. So then here the question is that, so which one you're gonna use? So as I said, implementing this will be the part of the first assignment, right? You can choose one of those three: mean predictor, and clean sample predictor, and the noise predictor. Which one you're gonna choose? One of the many reasons like why the diffusion model is basically more stable in terms of in the training is that we can do this. Basically, typically people use the noise predictor. Actually, there are some cases like using the clean sample predictor and the other things. But you're gonna see that for many of the cases, people use the noise predictor. Because of that, we know that the noise are basically the standard Gaussian samples, which means that these are really well normalized and also the scaled values. For the all the neural net training, you know that it's very important to basically do some kind of pre-processing in terms of normalizing all the input data set, right? Which means that you can say that these are naturally normalized as kind of the standard Gaussian samples. This basically also makes it very easy to basically train this kind of noise predictor using the neural network. So that's kind of one of the many reasons like why the training of the neural net, the diffusion model is quite stable. And that's kind of reason like why we also consider the noise predictor. We're gonna also see like what's the meaning of having the noise here. So in any case, basically with the noise predictor, it's the same thing. We just need to sample the XU, the time t, and also the epsilon t, and computing xt, and running the backpropagation with the alpha loss, the same thing. And based on this kind of the trained the noise predictor, what should we do in the generation process? I mean, in the reverse process, what we need to do is basically iteratively sampling the next one, starting from the x capital T all the way to the x0. We just need to sample the next one, the xt minus 1, xt minus 2, those things by computing the mean using the noise prediction. So at each step in the reverse process, what we need to do is that first basically predicting the expected noise here by feeding the xt and the t, compute this mean of that the reverse the transition the distribution here, and based on that, sample the xt minus 1. Repeat this until you reach to the x0, right? So you can see that actually this is also just like few lines of the code in the PyTorch. You just need to, starting from the x capital T all the way to from the capital T to the 1, basically predict this, running the bit code in the neural network, computing the mean, and then just like sampling the xt minus 1. Make sense? Literally just like few lines of the code in the PyTorch. You're gonna see that after all kind of the derivations, like lots of some details in the mess, you're gonna see that actually the implementation is super simple. So that's also the power of the diffusion models. Yeah, so this no. So as I said, since we can also compute the expected value of the x0 from the prediction of the epsilon t and the xt, we can see the whole process as kind of the refinement process. So that's kind of the key idea. Then here the one more quiz is that, so given the xt and also the predicted the noise here, what would be the estimate of the expected clean sample? So as I said, this is really something that you need to do. So every step, you're gonna get the xt and also the prediction of the noise. And then before we just go to the next step, we want to see what we're gonna eventually get at the end, basically for seeing the output from the xt, right? So you will be able to basically get some expected clean sample from these two information, right? So let's see how we can compute this. And here one question was that in the loss function like this, after we driving all the things, we basically drop this the weight, right? Then what's the point? Like, no, did we really need to basically follow all those kind of things, right? I recommend you really basically in your assignment 1, I recommend you really just try to put this weight, and having this weight might improve the training the convergence a little bit. So actually, for all the things you basically need to precisely have this like all the expression with this kind of weighting term, right? But you can also see that this weighting is only for basically weighting for each of the time t. So it means that like having this like the weight here is basically how much we're gonna basically put the weights for each of the time t. So actually, there are a bunch of the ways to basically replace this weighting in terms of actually we can also control the number of the samples of the time t. And also, if you train more and more and more, sufficient amount of time with the lots of the samples of the time t, then that becomes something that we can basically ignore this kind of the weights, right? Because we already have like lots of the samples for the old kind of the time t. So that's kind of the reason. Like this is like only depends on some kind of the time t, which means that how much we're gonna basically do some kind of the emphasis for each of the time step. And also that's true. For example, like for the almost the last step of the reverse the process, for the x1, for example, from the very starting from the x capital T all the way to the x1 to the x0, right? If you reach to the x2 and the x1, this will be already very close to the clean data sample, right? For those kind of cases, even when you stopped at that point, they might be already look close to the kind of clean kind of data samples. So it might be also interesting to see the graph of this kind of the weight and what kind of the weights that you're gonna see. Typically, you're gonna see that the weight for at the very beginning, and also at the very end would be kind of the small, because like whatever you sample there, it does not affect them much of in terms of like making some good trajectory. So that's kind of thing. One more thing is that, so as I said, this and also, yeah, you won't need to, you don't need to implement this part, but the first assignment will be basically simply working on the 2D data points. Because you will need to use the Google Cloud, you just need to, this simple kind of thing. And the basic idea will be basically starting from some kind of the unique Gaussian distribution in the 2D space. We are basically generating the one of the points in this kind of spiral kind of the graph. And I strongly recommend not just like solving this kind of problem, but also try to visualize all the things, the intermediate xt, and also the expected the output of the x0 as well. So what you get every kind of the time step. That might be very interesting to see. And lastly, let me get into this question. So in the fourth process, actually we modeled this like the transition distribution as kind of the Gaussian distribution. And based on that, we could say that, and also this like the whole the fourth jump from all the way from the x0 to the x capital T also becomes the Gaussian, right? Then the question is that when you also define this like reverse the transition distribution as the Gaussian distribution as well, does this mean that also this whole the likelihood distribution becomes the Gaussian? Yes or no? Yes? No? It looks like the answer is no, right? if the answer was the yes, then what's the point of like having the diffusion models, right? Because as I said, like the kind of limitation of the VAE was that we are modeling this as kind of the Gaussian distribution that is basically limiting the expressibility in terms like for the marginal distribution. The thing is that now we are basically defining this the likelihood of the distribution as kind of the sequence of this reverse the transition distribution. The difference between the fourth and the reverse process was that in the fourth process, the mean of the this distribution was the linear function with respect to the xt. So since the mean was the linear function, we were just multiplying some kind of scalar term here, right? To define this for the transition. So since this is the case that the mean is defined with some kind of linear function with respect to t, xt, we can see that the sequence of that also becomes another Gaussian distribution, right? But now what we are seeing for the reverse process is that we are predicting the mean of this distribution using the xt, which means that the mean is computed using the neural net, which will be typically non-linear function. I mean, if you make it as like the linear function, then it's the same. But you're gonna typically add some kind of the non-linearity into your neural net. So that's kind of the point. That is basically making the likelihood distribution becomes something more complex than the typical Gaussian distribution. Because of the fact that we are basically predicting the mean of that this transition distribution with respect to xt using the non-linear neural network. That is basically making some kind of the more complexity into our the likelihood distribution, and that allows us to capture some more the complex distribution of the marginal distribution as well. So that's the key idea in the diffusion models. While the kind of the big posterior distribution, the fourth process becomes of the Gaussian the distribution, and this is something that we are not learning, right? It's the predefined distribution. But based on that, we can still define each of the consecutive this kind of the transition distribution as the Gaussian, while the entire the likelihood distribution becomes something more complex than the Gaussian. So we are making the training of the learning of the reverse the transition to be simple as much as possible, while still basically having some the expressibility with the likelihood distribution by basically stacking this kind of the reverse the transitions. So that's the key idea in the diffusion models. Clear? No? Yes. So we have seen lots of the details in the math here. Actually, there are much more things that we needed to actually discuss for today. But I'm going to continue the discussion in terms of, so basically the thing is that we have seen these three options for the neural net training, right? The mean prediction and the clean data, the point, the prediction, and also the noise prediction, right? So the meaning of having the noise prediction is to make it the training to be easier and also faster. But we're gonna also see the meaning of the noise in the formulation and how this also can be connected to the score-based models. So we're gonna continue next Monday. Okay.